Let's talk about rectangular waveguide. But to answer the question, what is a rectangular waveguide? Let's just first define what is a parallel plate waveguide. So in a parallel plate waveguide, there are two plates which are parallel to each other. Let's define the dimensions. So suppose there is a parallel plate at y equal to d, and there is another parallel plate at y equal to 0, and on this side the length is infinite, and also on this side the length is infinite. The only finite length is d, which is the parallel distance of these two parallel plates. Also, this side and this side. These sides are not closed, they are open. So now we can answer what is a rectangular waveguide. In a rectangular waveguide, all four sides are closed. So there is no open side like the parallel plate waveguide. Also, the length on this side is infinite, but the length on the other two sides are finite. So you can think of a rectangular waveguide as a composition of two parallel plate waveguides. Now, to understand the properties of a rectangular waveguide, let's derive the equations that govern this waveguide. So let's derive the equation for transverse magnetic wave. If we can derive the equations for one, we can understand its behavior for all other kinds of wave. So in a transverse magnetic wave, AC is equal to 0 and EZ is not equal to 0. And from Maxwell's equation, we can derive equal to 0. So now our task is to solve this equation for EJ, and we are going to do that by a method of separation of variables. So we are going to assume that EZ, which is dependent on x, y, z, is defined by the multiplication of three functions, x, y, and z, capital X, capital Y, capital Z. And capital X is a function that is only dependent on the x coordinate. And capital Y is a function that is only dependent on the y coordinate. And capital Z is the function that is only dependent on the z coordinate. So we have separated the variables. And this makes the equation easier to solve. So let's put this solution in this equation. So if we do that, we'll end up with something like this. Since x, capital X, is only dependent on x coordinate, we are taking y and z in front of the derivative. Similarly, for y and z, we are taking the complementary coordinates in front of the derivative. Now we can divide both sides with xyz, and that will give us an equation in the following form, which is prettier to look at. Now, if we think about the rectangular waveguide as a superposition of two parallel plate waveguides, then we can kind of guess what will be the behavior of the wave inside this waveguide. So first of all, we know that inside parallel plate waveguides, the waves behave in a discrete manner. So you can either have a full wave or two waves or three waves. It comes in integer multiples, and we get standing waves from the solution. So something similar should come from solving this equation. So we should have a standing wave, some sort of standing wave, and it should have some properties of discreteness. Keeping these two in mind, we can write so we are writing this so that uh, these waves somehow superimpose and create a standing wave. And for Z, we know that it is a transverse magnetic wave. So in the Z direction, there is some propagating property. So it is not a standing wave in the Z direction, it is propagating in the Z direction. So from that intuition, we can write the solution for Z as a propagating wave. So this is the traveling wave. So now for the second property, we have satisfied this property. Now for the second property, we have to put in the value. So in a metal, the electric field parallel to the plates is 0. So electric field at y equal to d1, suppose this distance is d1. So at y equal to d1, electric field should be 0, the parallel part. And at y equal to d2, also the electric field parallel to this plate should be 0, and also to this plate and this plate and this plate. So if we put that boundary condition, we will get something like this. X equal to C2 sine X, Y equal to C4 sine Py, and Z equal to, which is propagating in the plus Z direction. So the total solution is C2, C4, C5 into sine X, sine By, and so we have all our standing wave and propagating wave together with discreteness. And since the electric field parallel to these plates are 0. From there we can get, just like the parallel plate waveguides, we can get that A equal to and B equal to